As someone pointed out, who was on the Facebook page, yes, I've written a children's story. It's called Loopy, the Spirit of the Cow Dog. And I've been invited by Watermark Books the Saturday after Thanksgiving to do a reading at Watermark Books. So if you're on the east side of town, if you've ever been to Watermark Books, okay? And the short version of this story, I wrote it. My dad died in October of '96, and following summer, I just needed to get out of the country, so spent a week in New Zealand and 3 weeks in the outback of Australia, and sat in a bar on a Saturday night and wrote the story in '97. Finally got around to getting it illustrated and published, and then I'm going to take the proceeds from the book and donate that to the Solar Fund. So it's just a little 6x9 book, but it's really, really well done. So it's about a little dog. It's all true. The dog showed up on the farm. It was a black lab that was about this tall, and it was a phenomenal dog. And even though it was a hunting dog, it figured out how to gather cattle. And so when we would gather cattle, the dog would run out and it would chase the cattle and help us bring it in. So that's how it got called Loop. And then it was Loopy. Then when it figured out it could chase cattle, then we changed the name of it to Loopy the Cow Dog. And so that's the whole basis of the story. So, and also, yes, so in various things to raise money for the solar project, one of the first big things I did was that I got this tattoo. Okay, so that raised about $4,000.
You got a tattoo?
How did that raise
I've never seen your legs.
Well, okay, Carter, I promise you, more people have climbed Mount Everest than have seen me in shorts. Okay, I promise you, more people have stood on top of Everest.
Not
Never.
even on the ranch.
No. So how the tattoo started was that this was the project was just kind of getting going, and it was right before Thanksgiving, and I was up. It was the first block. It was like this. I was lecturing, and two letters go sliding underneath the door, and of course my students lose all track, and they're focused on what the letters are underneath the door, and so I have to read them. So I'm reading and it was Thanksgiving, and a teacher asked students to write letters to teachers who had made a difference, and so I'm reading letters. And on the back side of one of the letters was this image. So they had drawn that picture on the back with me and the solar panel. And Nick Reiswig, who was sitting exactly where Keaton is, tell you exactly how it played out. He goes, "Man, you ought to get that tattooed on your leg." And I was like, "Or get that tattooed." And I said, "No way." Then he threw out the magic words. "How much money do we have to raise for you to get that tattoo?" And so I didn't want to lowball it, but I didn't want to set it at such a high mark that they wouldn't donate at all. So I'm kind of doing the mental math, and I said, $3,000. You raise $3,000, and you have until the start of graduation in May to raise the $3,000, and you pay for the tattoo, and I want a good tattoo. I said, okay, we're on. So initially, they'd raised about $2,200 as of the 1st of May. And so I'm thinking, I'm golden. I've raised $2,200, and I don't have to have the tattoo. It's good. But unfortunately then, because of social media, it got out, and this is the disadvantage of teaching brilliant kids, is that they go on to become engineers and doctors and lawyers and make a lot of money. And so then they heard that they were about $1,000 short of getting the money for me to get the tattoo, and then the money started pouring in, and then I had to get the tattoo. Yeah. And then last year, the challenge was so what would it cost for you to dye your hair? And it was okay, and it was red and green, right going into Christmas. And that raised about $5,000. So, yeah, so I've done various stupid things to try and save the world. So anyway, so the book, it'll.
Man, we got to come up with something.
No. I got the book this year. Okay, you and help out, buy the book. Okay, or tell people to buy the book. We'll have it at Woodard Mercantile down here. So, and we also have like solar merch. I'm working on getting that around if you want to support the cause that way. Yes, ma'am.
What day are you doing the reading?
Huh?
What day are you doing the reading?
It's the Saturday after Thanksgiving.
Are you planning on showing?
It's over at Watermark Books, so. But I'm also doing a book signing at Woodard's the following Saturday
Oh
after
my
that,
gosh, I
from
might
1 to
have to
3.
go get my book signed.
Huh?
I might have to go get my book signed.
I'm going though.
If you buy one, I'll sign one for you here, okay? So,
Okay, might have to.
all right. Anyway, so yeah, so it's kind of exciting. As a matter, just found out about it yesterday from Watermark Books that they want to do that, so. It's like shop local Saturday or something like that. And so anyway, so that'll be pretty cool. Okay, so let's chit chat about the lab, okay? And so what you should see is lab.
No, me.
So here's what you have to understand about what's happening on an atomic level. So here, for example, is methyl alcohol. Got 1 carbon, 3 hydrogens, and an OH group on it. So if you ever take a class called organic chemistry, you're going to spend a lot of time drawing structures like this. So basically what happens is this. And how you name organic compounds has its own little set of rules. So meth means 1. So if it was methane, which is a very potent greenhouse gas, that's CH4. Okay, so methane as a gas is CH4. If you take off a hydrogen and then put an OH group on it, then it becomes a liquid at room temperature and it becomes an alcohol. So by taking off a hydrogen and putting an OH group on it, you fundamentally change the structure. So methane as CH4 exists as a gas. Okay, and this is going to impact you all because methane is a very, very potent greenhouse gas. Methane actually traps more heat exponentially than carbon dioxide does. So everybody goes, oh, we got to reduce carbon dioxide emissions. Well, we do. But methane becomes even more potent in terms of the ability to trap heat within the atmosphere. At some point we'll talk about what's called a negative feedback loop. So basically, when you looked at your conductivity, did methyl alcohol conduct electricity? When you looked at your conductivity reading, what was the reading when you had methyl alcohol?
30.
Huh? 30, right? I said something, go ahead, 26, maybe 30, okay? Now, when you had an ionic compound, like when you had zinc nitrate, so when you had zinc nitrate, what was the conductivity of zinc nitrate?
29,000.
2,900?
500.
Huh?
500.
29,000?
29,500.
500, okay? Methyl alcohol is about 26. All of your ionic compounds are probably something around the high 20s, okay? So what that means is that fundamentally, when you're looking at conductivity, it's the ability for that solution to transmit electrons from one side to the other. So what happens is that methyl alcohol or deionized water, basically those electrons can't flow. So there's protons, electrons, and neutrons that make up methyl alcohol. But those electrons are all bound up, okay? Which means those electrons aren't free to carry that current across that solution. But when you take like the zinc nitrate, when that dissolves, okay, and this is important that you understand what's happening on a molecular level. So if you could shrink yourself down into that solution. So when I was preparing all of these, okay, all of these solutions, I started with a powder that I added to the solution and it dissolved. So zinc nitrate is kind of a whitish granular powder. So first off, let's start with the formula for zinc nitrate. So this is one of the things that you have to be able to do. So you go to zinc, zinc is 2+. Nitrate, NO3, 1-, okay? So in case you haven't figured this out, the golden rule is that you have to make the sum of these oxidation numbers add up to what?
0,
0. So knowing that, Miles, how many nitrate groups am I going to need?
2.
2. So this is going to be written as ZnNO3, 2. Okay? Why do we need the brackets in the 2? Why don't I just put ZnNO3, 2?
Because it looks like you have 32 oxygens.
Fantastic. I do that, it looks like I have 32 oxygens. I don't. I have 2 nitrate groups. Okay? So on the slip of paper that I gave you, with the polyatomic ions, okay, the highlighted ones are the ones that you need to have memorized. Today's Thursday, we're going to have a short quiz over those and some writing chemical formulas on Monday. Okay? So you have between now and Monday to have those ready. Now, if you notice, a lot of them are the same. Like you have nitrate and you have nitrite. You have sulfate and you have sulfite. Okay? Just remember your 8s have more oxygens than your ites. Okay? That's it. If you're into flashcards, make flashcards. Okay? Now, the reason that I had you keep your phones is all of it. I'm fairly addicted to this app. And I'd like to say, I wish I'd known this existed when I was in chemistry. No, I really wouldn't have gotten anything done. So there's an app called Write Formula. Okay? And it's pretty cool because it goes through and it's like a game. It keeps score. So it will tell you to, it'll say, okay, like, it'll have like sodium fluoride. So it'll either like give you the formula and you have to like click on the sodium and the fluoride, okay? And then it's going to ask you to name it and it kind of goes through that. So literally, I mean, I hate with all of my passion, okay, you have to understand, I hate video games, okay? I do. I don't play them, don't like them. My thought is at some point I have to give an accounting of my life and someone's going to say, you were given your life. What did you do with all the time I gave you? And I don't want to have to sit there and go, well, I spent 4 or 5 hours each day playing video games, okay? That's just going to be embarrassing. It's like, you were given this and this is what you did with it, is you played video games before, okay? So I hate video games to my very core, okay? But this is cool. So if you want to download it, it's literally, if you spend 4 or 5 minutes during each encore or whatever, you have a break and you do it, it's a cool deal. And it keeps score and, so, and it gets more and more complex. It starts off pretty simple. But it just reinforces this idea that, potassium chloride, KCl, and you have to name it. So if you want, you don't have to, but it is kind of a cool way to reinforce writing chemical formulas. So there are any number of things that are historic about you guys. One of the fact that in 32 years of teaching on 2 continents, I have never told a class to download an app and play a video game. So you are the first time I have ever in my life of teaching ever said that to a class. So, yeah, that's the story. So if that gives you any indication of how cool that game is, you guys have just witnessed history, okay? Tell your Uncle Paz, he won't believe it. So, all right. So here's what's happening on an atomic level. So any ionic compound as a solid exists as what we call a matrix, okay? So the zinc is bonded to, this is the solid form, okay? And then you got nitrates, and then that's bound to zincs, okay? And it forms this lattice of particles that are locked together. So to exist as a solid, sodium chloride, salt, you all have seen salt, right? There has to be these bonds that hold them together as a solid, okay? So, and they have to be relatively strong because it's a solid, okay? So basically what happens is this. You take this and you put it inside with the water molecule. Okay, so here's a water molecule. So which end of the water molecule, and at this point, this should now make more sense to you, okay? How many valence electrons does oxygen have? Miles. You can look on a periodic table.
Yeah, 6.
6, okay? So it has 6 valence electrons. How many does it want?
8.
8, because that's the most stable configuration. Mother Nature's the lazy prima donna. So basically what happens is this. Oxygen has a deficiency of 2 goats. Hydrogen has 1 goat. Hydrogen really doesn't care. It takes that goat, sends it over there. Okay? So that electron doesn't spend all of its time with the oxygen, but it spends the vast majority of it. Now, remember that hydrogen, if you think about it, is a proton and an electron. So basically what happens is that you have a lone proton out there on the end of that water molecule. So it's just a proton that's hanging out there. And then you got all these electrons over there. The proton's sitting there going, what did I do? You know, seriously, it's like it's been ostracized. You know, it's like, you guys are having this big party with oxygen. Y'all are hanging out there, woo, look at us, we're water, woo, we're important. Protons are out there going, dude, you know, come on. So this is kind of like the lonely positive end of the molecule, okay? There's nothing out there except for the 2 protons that are going, so, okay? And they're looking to bond, right? Because it's like, I'm kind of lonely out here. So you have all these water molecules, and the water molecules themselves are bound together, and we know that because it's a liquid. So you have a difference in bond strength. So you have a zinc nitrate, that powder, that exists, and there's that lattice that hold those together. There's bonds that hold the water molecules together, and that makes it a liquid. Okay, so basically I take that, I scoop some in, it begins to dissolve. Just like adding salt to, you're going to make soup, and you put in salt. Oh, it's going to dissolve. So what happens is that the nitrate has a choice to make, okay? The nitrate has a choice to make. It can either stay bound to the zinc, okay, which is an option, or because the nitrate is a negatively charged polyatomic ion, which end of the water molecule is that nitrate going to be attracted to? The positive proton end or the negative electron end of it?
Positive.
Positive, because opposites attract. So at this point it's a tug of war. So the nitrate's sitting there going, man, that zinc nitrate has been sitting in that shelf for years, okay? It's been sitting in our storeroom, okay? They've been together for a long time. But that nitrate's going, man, zinc, man, I've been with you for a long time. We've been through a lot, okay? We've been sitting here on this shelf and just kind of hanging out. They've talked and, you know, they've bonded. They're shaded pictures, taking selfies and everything, right? So the nitrate comes along and says, deuces, I'm out. So it breaks the bond with the zinc, and it comes over here and it bonds on the negative end of that water, or the positive end of the water molecule. At this point, the zinc goes, well, heck, what am I going to do? Zinc says, well, if you're breaking up, I am too. So the zinc says, hey, I'm positively charged. So the zinc says, hey, I'm going to go party with all the electrons, okay? They're negative, but there's a lot of them, okay? So the positive end attracts the nitrate. The zinc attracts to the positive, or the negative end of the water molecule. And these bonds here, okay, are stronger than the bonds that hold the zinc and nitrate together. Because if these bonds were stronger, then it wouldn't dissolve when you put it into the solution. So, like when you all wash your hands, which hopefully you do quite often, when you all wash your hands, you're putting your hands in water molecules. Then the water molecules have a positive and negative end of it. So this positive and negative end of the water molecules are attracted to the atoms that make up your skin. Now, the atoms that make up your skin are going, we're tight, okay? Your skin doesn't dissolve because the bonds that hold your skin together are tighter than the bonds that it could form with water. And that's why it doesn't dissolve, okay? So it's always a tug of war. So when something is soluble in water, that means that the bonds that it forms with the water are stronger than the bonds that hold it together, okay? Got that visual? So now on an atomic level, here's this water molecule. It's got the zinc ions up here on the around the negative end of it. It's got the nitrates over here. And these are charged particles. So along comes a flow of electrons, okay? So electrons have to hop. They have to hop from one thing to another, to another, to another. And so because of the fact that these electrons are able to move across these charged particles, that means that's very, very conductive, okay? So anything that's an ionic compound that dissolves in water is very conductive because you have these charged particles that allow those electrons to transfer across. Now, if you go back to methyl alcohol, okay, like this, also has protons, neutrons, and electrons in it, because that's what everything's made of. Okay, there's a revelation. But those electrons, when you try and pass a current across it, they go. I don't know why my lecture from yesterday just randomly started to play. Okay. If you want to hear a momentum lecture from AP physics class, it was that. So, this is also made of electrons. But these electrons are tight, okay? Because these are covalent bonds. And covalent bonds are formed by just sharing electrons. So, this exists as a liquid, and there's electrons in it. But this doesn't have the charged particles that allows that current to flow through. So what I wanted you to see is that when you have pure water, okay, deionized water, that doesn't conduct electricity, mainly because of the fact that there's no charged particles within that to carry that electricity across. Now, what did somebody get for your conductivity when you use tap water?
949.
What'd you get?
949.
949? About 1,000, okay? So when you have deionized water, that conductivity, I'm guessing, was what, around 25? That's typically where it is, okay? So pure water doesn't have that capacity to conduct because they're water molecules. They have electrons, but those electrons aren't free to transmit that current. But when you use tap water, it does have some dissolved ions in it, and that's what allows that to conduct. So if you're given two solutions and you're trying to figure out, hey, what's a simple test that I can see whether it has ions in it? Put a conductivity probe in it. The more that conducts electricity, that's an indication of the number of electrons that are available to transmit that current. Okay? Does that make sense? Now, what happened when you diluted what did you dilute? Sodium nitrate?
Mm-hmm.
Okay? What happened as you diluted that? What happened to the conductivity?
It went down.
It went down. So if you were to draw a graph, so let's talk about a graph. If you were to draw a graph of molarity versus conductivity, okay? And there's 0, and there's 0.1, there's like 0.5, and there's like 0.1, way out here is 0.2. So if you were to draw a graph of molarity versus conductivity, what would that look like? Mr. Grove.
The lower the molarity, the higher the conductivity.
You want to stick with that answer?
Yeah.
Lower the molarity, the higher conductivity. I want to make sure that's what you said.
Yeah.
Okay, you want to look at your data and reevaluate that answer?
Oh, wait. Higher the molarity, the higher the conductivity.
Okay. So here was like 30,000 on your conductivity, right? And here's like 0. So if you were out here at 0.2, that's when you had your, so look at this. if the molarity of the solution is 0, you basically have pure water. What was the conductivity of pure water? 26, right? So basically 0. At 0.2 molar, you were out here at 30,000. So it's going to go something like this. Now, think this through. Why, as you have a higher molarity, why did that have a higher conductivity?
There's more electrons.
Yeah, there's more stuff to carry the current, okay? Because as you dilute it, if you think about it, you're making it more and more like pure water. Pure water has no conductivity, okay? So that's why. So as you go through, as that concentration becomes higher and higher and higher, the conductivity becomes more because there's more, like Miles said, there's more particles there to transmit that current. There you go. Okay? Cool with that. All right. So when you got to question number 6, when you put 3 drops of the potassium chloride into the methyl alcohol. So what did somebody say on that? Parker, what did you predict was going to happen on number 6?
I said it would conduct a small amount of electricity.
Why?
Because, what was it? The potassium chloride is conductive, and so there's a small amount of it to conduct electricity in the solution.
Okay? So what did you get when you actually did it? What was the conductivity?
We did not do it. Because I didn't see the question. So we didn't do the...
Okay. Well, here, let's do that right quick.
You told us not to do the question. Oh, jeez.
Ah.
You told us not to do the.
So we'll test the methyl alcohol by itself. And it has a reading of 32. Okay? So that's our baseline. So the methyl alcohol by itself had a conductivity of 32. Just gonna hold that for a second. Okay? So we're going to add, was it 3 drops?
Yeah.
So we'll go 1, 2, 3. Okay. So kind of add a little bit of a stir. So now we'll check that conductivity again. And now the conductivity, anybody care to guess the number?
500 million.
I'll give you a hint. It's less than 1,000.
999.
Huh?
400.
Less than 440.
Whoa.
335.
Less than 320.
36.
Higher than that.
92.
Higher than that.
150.
Higher than 100.
150.
180.
Higher than 150.
260.
Higher than 180.
290.
Higher than 190.
200.
Higher.
205.
Higher.
239.
250.
239. Ethan wins.
Ethan
So.
Ethan won.
Ethan wins. All right. So here's the deal. So what we did is exactly what Parker said. So we had methyl alcohol, which acted as a barrier to the conduct to that electricity flowing across.
239.
We added some charged particles to it. Now, Mr. Grill, if I keep adding potassium chloride to it, what do you think is going to happen to the conductivity?
It'll get higher.
So what would the graph look like? If I graphed drops of potassium chloride versus conductivity, what would that look like?
The more drops of potassium chloride, the more conductivity.
So maybe a positive correlation, direct relationship?
Yeah.
Fantastic. There you go. Okay. Kyle the Graph Grill. That's your new nickname, man. Kyle the Graph. Okay. Could have worse. Okay. Anyway. So,
Not Kyle.
are we good? Alan. Taught Kyle last year. Sorry. I've been the whole year and haven't called you Kyle. That's okay. I'm doing pretty good. Okay. So, I know what it's like to be the youngest of 5 kids, so I was forever called my brother Scott. So, okay, are we good? Anything else on the lab? You got nice data tables? I'm gonna be impressed. Huh?
I can't rely on someone's data. Okay.
Okay, going once, going twice, any questions, sold? Get those handed in.
Addie, get Carter's data table. We need it. Ours is fine. Addie says us is getting. No, it's not. It's not fun, but I don't care.
Before you change it.
I haven't changed it. It's like 3949.
3,900.
Oh yeah, the rest of ours are fine. No, they're not. Yeah, I refuse. Please, just for a little bit. I was in here. Just for a little bit.
What do you mean you weren't here?
I wasn't here.
And how do you have all this?
I copied that, but like the data's all really bad.
Yeah, our data's fine, other than.
No, it's not.
Other than the purple alcohol, we did great. Look, we were there.
I refuse.
You know, I never did my data.
What?
Which
Which one's 6? Question 6? What are you talking about? Question 6?
Yes.
I gave my reasoning why I thought it would do that. That's literally like an opinion-based thing.
Fight. Mr. Burkett.
What?
Mr. Burkett.
What?
You want to check it?
Huh?
Hey, connect it to a ruler right quick. You can look at this.
What?
Data table.
Yeah?
Abigail refuses to trust her data.
No. The magnet.
Oh, okay. Can I come in too?
Oh, it's a strong magnet.
Data is okay. How do you know?
Maybe you can like bend it too.
Actually, we
Here. Oh, I was saying if you bend it all the way back, it'll let go. It's simple. It doesn't let
Wait,
go.
you like it bends this.
It bends it. I can bend it all the way back.
No, it isn't. I compared it to what's his name.
You can break the ruler before that thing
See?
comes off.
But we got 31 from alcohol.
At least on mine.
No, you didn't. You got like 3,000
These
something.
numbers should be like in the high 20,000.
Told you. But like that's close enough. No.
You're off by, no,
Look at this.
no.
Wait, maybe
That's
it's-
like saying, you owe me $20,000 and you only give me back 4,000. No, that's not close enough.
Okay, you know what?
It's like these numbers. It's like saying.
I think you did
Black
have
your
to
water
say,
bottle. Black your water bottle. Let's hear the noise.
It's not all my fault.
Oh, dang it. I missed it.
I wrote that.
I don't know.
okay. Step away from the rule. Step away from.
I'm sitting down. How am I supposed to step away from it?
In physics, we study potential energy. Okay. So, are we still going with the camera?
Yeah.
Okay. So she can watch me stare at you.
Yeah.
Okay. So that's it's funny. Some teachers just like I'll tell them like I record my live lectures and they like flip out. It's like, oh my God, you record your live lectures? Yeah, I don't care. Okay. So get out that packet because we're going to kind of work through that thing and what I want done. So we're going to kind of start through this whole thing together. So now we have the basic idea of writing chemical formula. And in case you haven't figured out, when you write a chemical formula, there's 2 general rules that we have so far. Rule number 1, which one do you write first, the cation or the anion? Cation, okay? You always write the cation first, the anion second, okay? No exceptions whatsoever. You are never going to call sodium chloride sodium, okay? For whatever reason, it's just stupid, right? So always write the cation first, the anion second. No exceptions whatsoever. And here's the other most important rule. If you write the chemical formula correctly, listen to me very carefully what I'm going to ask. what is the sum of the oxidation states? 0. So the sum of your oxidation numbers has to equal 0. Not pi, not -1, not 5, okay? This is 0, okay? And the reason that is because Mother Nature is a lazy prima donna. And when that happens, you form the most stable compound because that's at the bottom of the energy curve. Mother Nature is a lazy prima donna. So up here on the top of page 7, okay, so I want to make sure everybody's cool with how this thing is going to work. Because what we're going to do now is we're going to get more into the mechanics of why it works. And then up to this point, I have given you the names and asked you to write the formulas. Now we're going to make the door swing the other way. Now we're going to start to give you the formulas, and you're going to have to write the names. Okay? So the door has to be able to swing both ways. So to do that, you've got to figure out, hey, what's going to be the most likely oxidation state on these particles? So for example, and this is where you have to have your periodic table. You cannot do this without the periodic table. So you're going to have Cl. Okay, so up there on at the top of page 7, you're given the element chlorine. So the first thing that you have to decide is chlorine going to form a cation or is chlorine going to form an anion? That's the first decision that you have to make. Now the beauty of this is that when you look at the periodic table, what are the only elements that are going to form anions? Metals or the nonmetals? Nonmetals. And those are up here in the far right-hand corner. Everything else is going to form cations because they're metals. Okay? So it's actually a very small percentage of the periodic table that is actually willing to form an anion. The vast majority is going to be cations. So you have chlorine. So there's a couple of ways you can think this through. I'm just going to show you some options. You figure out the method that works best for you. Some people like to do Lewis dots. So how many valence electrons does chlorine have? 7. It's a halogen, right? So it has 1, 2, 3, 4, 5, 6, 7. How many does it want? 8. So is it going to lose 7 goats or gain 1 goat? It's going to gain 1 goat. So that when it becomes a goat, then it becomes Cl1 minus. Now, once it becomes, now listen to the terminology. Is chlorine a monoatomic or polyatomic ion? Mono. But it has 2 letters. Yeah, it's still an element, okay? Even though it has 2 letters, don't look at that and go, oh, chlorine, that's polyatomic, it has 2 letters. No, it's just chlorine, okay? So don't look at that and go, oh, it has 2 letters. No, bad. Robin, what are you doing? Whatever. Okay, so this is where you have to understand the vocabulary. Because it's a monoatomic anion, when you write the name of it, what do you change the ending to? IDE. So this has become chloride. Okay? Now, if you don't want to mess with the dots, just find it. So here's your other option. Figure out where it is on the periodic table. Oh, it's a halogen. It has 7 valence electrons. It wants to become like argon, the noble gas to the right. It has 7. It's going to gain 1. That's the other thing that you can do. So you can either look at where it is on the periodic table or do the Lewis dots. Yes?
So like,
Izzy.
how do we like decide what ending we're supposed to put again? Can you like
Okay, so here's the deal. The only time you change that ending to IDE is when you have a nonmetal, oxygen, sulfur, nitrogen, phosphorus, something like that. And as an element, it's chlorine, it's oxygen, whatever. But once it becomes an anion, then you change that ending to IDE. Okay, so once it takes on those electrons, then you change that into IDE.
And are there other rules too for
No.
like other endings? That's it?
That's it.
Okay.
The cations, you never change the name. Okay?
Okay.
It's only the anions that change into IDE.
Oh, so only the negative ones.
Only the negative ones.
Okay.
Only the negative ones. Okay, so similar type story. Luke, you're the oldest, right? So, in the region that I was at in Peace Corps in Africa, the people there, they were called the Ikalunga people. They had a cool tradition. And you're going, what does Africa have to do with naming anions and Luke? So I taught Luke's mom way years ago about in the portables over there. And so in the Kalunga tradition, when a woman becomes a mother, she no longer goes by her name. She becomes Ma, and then the name of her oldest child, because they put such importance on becoming a mother. So once Luke was born, his mom would become known as Ma Luke. So it's Ma, and then the name of the oldest child. That doesn't happen until you become a mom. So if any of you are like the oldest, then it would become, Ma, and then that name. So the same thing happens with anions. Once they gain that electron and they become an anion, then we change that ending to IDE. Okay, so you look at nitrogen. So nitrogen is a little bit of an anomaly. So, Luke, how many valence electrons does nitrogen have?
5,
5. How many does it want?
8,
So what's it going to gain?
3.
So this becomes 3 minus, okay? So once it gains those 3 electrons, you change the name, and now what are you going to call it? Instead of nitrogen, we're going to call it nitride, okay? Now, nitrogen actually is a little bit, it's tough to actually gain those 3 electrons, so you actually don't see very many things bound up with pure nitrogen. You're going to see it much more likely to be bound up with nitrates or nitrites or something like that. It's rare that things actually bond with nitrogen. Okay, so let's look at S, sulfur. Raman, how many valence electrons does sulfur have?
6,
How many does it want?
8,
What's it going to do?
gain 2.
So that's going to become 2 minus. So how are you going to name it?
For what?
Once it gains the 2 electrons, how are you going to name it?
Sulfide?
Sulfide. Okay? Now, let's look at D. You have potassium. Okay? So, Izzy, what's potassium going to do?
Potassium is gonna lose one.
So it's going to become,
Positive.
so we're going to call it potassiide?
Potassium. That's it.
Yeah, it's just potassium. Okay? So it's just potassium. It's still just potassium, even though it's lost an electron. Okay? You have boron. Okay? So, Ella, how many valence electrons does boron have?
3.
3. Is it going to gain 5 or lose 3?
Lose 3.
So it's just going to be 3 plus. Are we going to call it boride?
Oh.
No, it's just still boron. Okay? Boring, boron. Anyway. Now, what's going to happen with neon? Miles, what's going to happen with neon?
It's just gonna stay neon
It's just going to stay neon. Why?
because it has 8 valence electrons.
Yeah, it has a noble gas arrangement. It's not going to do anything. Okay? We're good? Okay. Now, down below on those critical thinking questions. Okay? At this point, you should be able to answer those without any hesitation. Okay? You've seen the patterns. That first question, consider the formula of chloride. Tells us 1 sodium, bond to 1 chlorine. Overall charge is 0. Positive, negative, neutral. So there's charged particles, but the whole thing has a charge of 0 because it's neutral. Okay? Same thing happens with magnesium fluoride. And again, at this point, hopefully what you have is a couple of different tricks that you can look at this. And the more ways you can look at these, the deeper your understanding is going to be. So like when you get down to number 2, magnesium fluoride, okay? So one way I want you to be able to think of that is going, oh, magnesium has 2 valence electrons. Fluorine has 7. Okay, that's cool. Yellow. Okay, I'll send her. Emma, run out of the office. Your mom has something. If they're cookies, I expect you to rinse them back. Okay. So, one way that you should be able to look at magnesium fluorides, you can, oh, look at the valence electrons. Magnesium has 2, fluorine has 7. 7 goats, I need 8. It's going to take 2 groups of goats to get rid of the 2 from the magnesium. That's one way you can look at this. You can also look at it and go, okay, hey, I'm a math person. Magnesium is 2 plus, fluorine is 1 minus. I bring that 2 over there, I take that 1 over there, I get MgF2. If you like that stuff. Or you're a math person, you go, oh, I want the sum of the oxidation states to equal to 0. I have plus 2. I have 2 fluorines at -1, that's -2. 2 plus -2 gives me 0. The more ways that you can think these through, the deeper your understanding is going to be. But what I don't want you to do, I beg of you, just don't get locked up in the mechanism of it. Think through why this is happening, okay? Because if you understand the rationale, and then it's like, oh yeah, Mother Nature's a lazy prima donna. That puts us to the bottom of the energy well. That's why it forms this. If MgF was stable, guess what? Mother Nature would form MgF, okay? But it's not stable because that's plus 2, that's 1 minus, everything adds up to -1. Mother Nature goes, not digging it, okay? Don't like that. It's not stable, okay? Mother Nature wants to go to the bottom of that energy well. And that's why it's MgF2, so that the sum of those oxidation states add up equal to 0. Does that make sense? Okay. Now, when you get over to that next one's on page 8, okay? So, down here, basically, what we're going to be talking about here is this whole thing that it's just a summary of what we've got. Now, when you get down to question number 6, it says, there are 2 rules to follow when writing formulas for ionic compound. One has to do with charges, and the other one, which atom do you write first? So, your answer to number 6, rule number 1, if you want to shortcut it, and if you're a math nerd, we use this a lot, it's the Greek letter sigma. Anybody know what that means? Ever seen this in your math classes before? Okay, it just means sum. Okay, so sigma is the shortcut version of sum. So rule number 1, you could put the sum of the oxidation numbers equals 0. Okay, that's it. That was the summary. That's it. Make the oxidation numbers add up equal to 0. And that's rule number 1. Rule number 2, you put the cation first. You put the anion second. Okay, those are 2 rules. That's it. You keep those in mind. Everything else takes care of itself. So when you get down to question number 8, okay, so I want to go through a couple of these. So at this point again, you have some options on how you can do these. So let's say, for example, you have that barium and sulfur. So what I would recommend, this is what I would do. Literally, if you gave me this and said, Burkamp, write the formula for the combination of barium and sulfur, okay? This is exactly what I would do. I would look at barium, oh, it's group 2, or you can look on the periodic table that I gave you that has the chart on it, okay, that has all the ions listed. And I'd sit there and go, okay, barium is 2 plus, that's cool. Sulfur has 6 valence electrons, that's S2 minus. Barium wants to get rid of 2 electrons, sulfur wants to take in 2 electrons. What's the formula going to be? BAS. BAS. Okay? There you go. That's all you have to do. Now, here's what I want you to avoid. Okay, listen to me very carefully. If you're into the cross-step method, which some people like, that's cool. But when you have a situation where they both have the same charge, don't do this. Don't take this 2 and move it here and take that 2 and move that there and write that as Ba2S2. these always want to be in like the simplest whole number ratio, something called an empirical formula, okay? So we'll talk more about empirical formulas. So empirical formulas just mean that they're the simplest whole number ratio. Ba2S2, you can reduce it down. So that's why you're going to write that as just BAS, okay? That's it. Now, one that's a little bit tricky is when you get to something like D where you have oxygen and aluminum, okay? So this is kind of as complicated as it gets. So you have oxygen at 2 minus, you have aluminum at 3 plus. So Keaton, what's the formula for this going to be? Al2O3. Take that 3, boom, take that 2, move that. Okay? That's the simple process. Oh, here's aluminum oxide. Now, a word of caution. If you're going to do the cross step and you're going to put those oxidation numbers up there, and you can use those to figure out the formula, but when you write the actual formula itself, don't put the oxidation states up there, okay? Don't put aluminum at 3 plus, oxygen at 2 minus. That's true, but when you're writing the formula, don't include the oxidation states. You can use the oxidation states to figure out the formula, but don't actually write them down. Now, Carter, how can I check that that is the correct formula for aluminum oxide?
Lewis dot.
Huh?
You can do the Lewis dot.
I could, but that's a god-awful amount of work. What did the sum of the oxidation numbers have to equal?
0.
0. So here's how I can check that this is right. Each aluminum is 3 plus. You can look at the periodic table and figure out that it's 3 plus. You can look at your periodic table with the list chart of your ions. You can figure it out there. Oh, I take 2 times 3 plus, I get 6 plus. Oxygen is 2 minus. I've got 3 of those. That gives me -6. Everything adds up to equal to 0. So there is really no valid reason to have an ionic formula that's wrong. See if they add up to equal to 0. Okay? That's all you have to worry about. Now, let's talk about number 9 down below. This is going to be one skill that you have to begin to develop. And this is a skill that you're going to use when we figure out when we begin to write the names. Okay, so this is like a sub-step. So I want to make sure everybody's cool on number 9. So you have X2S. Okay? What you're trying to figure out is what's the charge on X. Okay? Now, I want to show you 2 ways you can do this. You pick the method that works best for you. Okay? So, one option is that you do the reverse cross step. Okay? So you take this 2 and you move that up there and realize, okay, that's sulfur, which should make sense. Sulfur's in the same group as oxygen. It has 6 valence electrons. It wants to gain 2. Okay? So out here, how many sulfurs do you have? 1. You move this up here. X then has a charge of 1 plus. Okay? So that's one option, is that you do the reverse cross step. If you're a mathematical person, okay, you can actually write this as almost like a formula. And you can go, oh, sulfur, I want everything to add up to 0. So I know sulfur is -2, okay, right? So if you are a math nerd, here's your simple formula. I've got 2 of my x's. So literally, 2x plus a -2 has to add up to equal to 0. So if you're a math nerd, okay, you're a hardcore math nerd, here's your equation. 2x plus -2 equals 0. So how are you going to get x by itself? Ella.
5 by 2.
No, I got to do something first.
Well, you have to add 2 and then divide.
Yeah, so I get 2x equals 2, then divide by 2, x equals 1. I don't care. Pick the method that works best for you. Now, when you get to MgX, now, here's what you're tempted to do. Here's what you're tempted to do. Oh, I have one magnesium, and I have one X, so X is -1, magnesium is +1. Keaton, is that right? No, why? Magnesium is +2. So start with your cation. Your cation is going to be Mg2+, because you know that value. So that Mg is 2+, but it's in a 1-to-1 ratio. So here's another, let me give you a hint, okay? Let me give you a hint. Anytime you have an ionic formula that they're in a 1-to-1 ratio, what do you know about the oxidation numbers? If you have an ionic, think this through. If you have an ionic compound and they're in a 1-to-1 ratio, what do you know about the oxidation numbers? Ethan.
Say that again.
Okay. I have an ionic compound, like for example, MgO. They're in a 1-to-1 ratio. Okay? So what do you know about the oxidation numbers? Are they the same or are they different?
They should be the same.
They're going to be the same. They're going to be equal and opposite. So that means this magnesium is 2+, that oxygen is 2-. So whenever you see, now listen to me very carefully, listen to me very carefully. When you have a 1-to-1 ratio, that doesn't mean that that it's +1 and -1. It could be +2, -2. It could be +3, -3. Okay? So when you have a 1-to-1 ratio, all it means is the oxidation states are equal and opposite. It doesn't mean that they're both 1. It just means that they're equal and opposite. So when you get to 9C, you have X3P2. This is as complicated as it gets. But again, if you do the reverse cross step, bring that 2 up there, take that 3 up there. Phosphide gains 3 electrons because it has 5 valence electrons. That means this X is going to could be magnesium, it could be calcium, any number of things. All you know is that it has a charge of +2. Good with all of that? Okay. Now, when you get over here to the polyatomics, okay? So this lists a lot of the polyatomics that's also listed on your sheet, okay? Some of these we will use a lot, like I said. Nitrate, we're going to use that so much. We're going to use sulfates a lot. We're going to use hydroxides a lot. We're going to use phosphate some, okay, 3-. Those 4, without doubt, are the ones we would use most often, okay? Not all of them, but those are the ones we're going to use most often. So, when you look at the polyatomic ions that have a suffix of 8, okay, here's what I want you to see. There's 8s and ites. All I want you to remember that 8s always have more oxygens than the ites. So, sulfate is 2-. It has 4 oxygens. Sulfite is SO3. It has 3 oxygens. Nitrate, 3 oxygens. Nitrite, 2 oxygens. Okay? So your 8s have more oxygens than your ites. Okay? Just remember that. So, when you get down to over here to page 10, okay? Let me give you a word of advice. Number 6, up there on the 6, all you're going to do is write the names. Now, initially, this is something new. Up to this point in your chemistry journey, all I've done is given you the formula. Excuse me, I've given you the name and asked you to write the formula. So now we're going to make the door swing back the other way. Now you're going to be given the formula and you're going to be asked to write the name, which isn't horribly difficult. So if you look at that first one, you have Na3PO4, okay? Now, we'll get more into this later, but all of these are ionic compounds, okay? So when you name this, the door has to be able to swing both ways. So clearly you have sodium first, right? So you're going to have sodium phosphate, okay? That's all you have to do. Now, here's what you're tempted to do. And I've seen this, and do not do what I'm about to do. Okay, do not do what I'm about to do. You're going to look at that and go, oh, there's 3. Maybe I should write sodium 3 phosphate. Okay, that's what you're tempted to do. Okay, now Raman, you smile and you shake your head no. Why?
Oh, I don't know. I'm just doing that. I'm praying.
I'm praying. Parker, what's wrong with that? Why do I not need to put the Roman numeral 3?
Because the number 3 means that there's 3 sodium atoms.
Yeah. And also, what's the only time you put Roman numerals?
If there's multiple oxidation states.
Yeah. All your group 1s, all of your group 2s, your alkalines, your rare earth metals, they don't have more than one oxidation state. So this is where the door has to swing both ways. If I just gave you the name sodium phosphate, could you take sodium phosphate and end up at Na3PO4? The door swings both ways. So when you get to, like on B, so Luke, how are you going to name B? Top of page 10.
Ammonium sulfate.
Yeah. Because you have NH4, 2, SO4. Go to your chart. Hey, there's ammonium. So just go ammonium sulfate. Okay? Now, you don't have to worry about the 2 because when you reverse the process and you write the formula, oh, it's ammonium sulfate because sulfate is 2 minus, ammonium is 1 plus. Okay. You should be able to do those without giving it any thought. Now, let's talk about 7C. You have barium hydroxide. I want to make sure everybody's cool with this. You have barium hydroxide. Okay? What's the oxidation state of barium?
+2.
Plus 2. So you have Ba plus 2. Hydroxide is
-1.
OH1 minus. So it's just this can be BaOH2. Is that cool?
No.
Emma, is that cool? For barium hydroxide, BaOH2.
No,
No, horrible. Why?
because you don't have, the way you have it, you only have 2 hydrogens, you don't have 2 oxygens.
Yeah. So what do you have to do?
Put it in parentheses.
Put it in parentheses. Okay. Now here's what I don't want to see. Okay, I've seen this happen. Do not do what I'm about to do. Let's say that you're going to have, I don't know, potassium hydroxide. Okay. So potassium is 1 plus, hydroxide is 1 minus. Don't do this. Okay. That's just going to frustrate me to no end. Why?
Because it already has 1.
Huh?
It only needs.
Yeah, it only has 1. Only put brackets when there's more than 1 polyatomic ion. Potassium hydroxide is just KOH. Okay? Don't put the brackets around it. All right. Now, here's where it gets dodgy. Okay? Over on page 11. This is what's going to require the most thought. Okay? Yes, I said the T word, thought. Okay, shocking as that may be. Where this, and this is going to form the basis of the lab that you're going to do tomorrow when you have things that have more than one possible oxidation state. Here's the deal. When you look at, when you're going to name these formulas, when you have cations that have more than one possible oxidation state, you have to write out and figure out what the numerals are. That's what's going to require the thought. So if you look at the top of page 11, you have CuCl2. Okay? Now, here's what you're tempted to do. You're tempted to go, oh, this is just copper chloride. Okay? That's what you're tempted to do. But here's the problem. If I go into that into our chemical storeroom, I want to have two different bottles. I'm going to have copper 1 chloride and I'm going to have copper 2 chloride. I don't know which one I want. Okay? So when you have more than one possible oxidation state, and where is, give me that other periodic table. Here's fantastic. So if you don't know whether or not to put Roman numerals, okay, you cannot tell just by its location in the periodic table. All of those that have more than one oxidation state are in the middle of the periodic table. But just because it's in the middle of the periodic table doesn't mean that it has more than one possible oxidation state. So if you're not sure, let's say, for example, you're dealing here with copper. Come up here, and if you can find copper or that element and it has a Roman numeral after the end of it, that means that you have to put the Roman numerals. If it doesn't have a Roman numeral, then you don't have to worry about it. Okay? So if you're not sure, go to here. Find it. If there's a Roman numeral, put the Roman numeral. If there's not a Roman numeral, don't put the Roman numeral. Okay? Pretty straightforward. So here's what you got. So what you want to be able to do is make the door swing back the other way. You have to figure out the charge. So here's what I want. Here's the easiest thing to do. Take this 2 and move it back up there. Take that 1 and move it here. So what this tells me is that this is copper 2 chloride. Now, here's how you can check that you got this right. Take the name copper 2 chloride and write the formula. If you can take copper 2 chloride and end up at CuCl2, you did it right. Now, what do you think, given CuCl2, what do you think the most common mistake is made when you write the name of copper of CuCl2? What do you think the most common mistake is? Parker?
Putting the Roman numerals in number, like that, it just being a 2. I don't know.
Kinda. Here's what people do wrong most. They're going to look at this and go, oh, I have 1 copper. And they're going to write it as copper 1 chloride. Okay? Because they're going to think the Roman numeral indicates the number of atoms. But does the Roman numeral indicate the number of atoms?
No.
What does it indicate? The oxidation state. Okay? Because here's the deal. If you wrote it as copper 1 chloride, let's say I write down copper 1 chloride, and I give that to Peyton. I say, hey, Peyton, I want you to write the chemical formula of copper 1 chloride. Peyton's going to go, oh, that's CuCl. Because Peyton realizes, oh, the 1 is the oxidation state. So if I write it as copper 1 chloride and I reverse the process, it's train wreck. Now, where it gets sketchy, okay, here's the sketchy one, is when you have something like FeSO4. Okay? Now, here's what you're tempted to do. Oh, this is a 1-to-1 ratio. Iron, 1, sulfate. That's what you're tempted to do because it's a 1-to-1 ratio. What you have to do, listen to me, listen to me, listen to me. Your anions never have more than 1 oxidation state. Start with the oxidation state of your anion. Ella, what's the oxidation state of sulfate?
2-.
2 minus. So sulfate is 2 minus. What's the charge on my iron going to be? Carter. Carter, you're making this difficult. Do not make this difficult. Carter, what does the sum of the oxidation numbers have to equal? So if this is -2, what does the iron have to be? 2 plus. Okay? Or they're in a 1-to-1 ratio. If they're in a 1-to-1 ratio, what do you know about the oxidation states? They are automatically equal and opposite. So this is just going to be iron to sulfate. Okay? Got that. So here's the difference though. When you look at Fe2, SO43, look at that one. Again, reverse the process. Take this 3, move it up here, take that 2, move that over there. This becomes iron 3 sulfate. So what requires the most thought, trust me on this one, what requires the most thought is writing the names of ionic compounds where you have Roman numerals. That requires more thought than anything. Okay, so what you should be able to do, and what I want you to get through, is by tomorrow, get through the bottom of page 12. So we've got a lab tomorrow on oxidation states of manganese. So we've got a lab tomorrow, quiz on Monday. Okay? It's not going to be very long, but by Monday, here's what's going to be on the quiz. I'm going to give you the formula, write the name. I'm going to give you the name, write the formula, and you're going to have to know your polyatomic ions, the formula and the charge. Okay? So, there we go, kids.